Hello, everyone, and welcome to Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenter today is Timofey Golubev. Timofey is a senior research scientist at Thermal Analytics, where he works on the development of both physics-based and data-driven models for multi-physics phenomena. His focus areas include thermal electrical modeling of photovoltaics and batteries, conjugate heat and moisture transfer, and human thermal modeling. Timofey received his PhD in physics from Michigan State University, with his doctoral research focused on photovoltaic modeling, and has been a part of the TAI family since 2019. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. We are also recording this webinar, and we'll be sending you the link following this presentation. And with that, Timofey, if you're ready, you may begin.
Hello, everyone. Today's webinar is on modeling the impact of thermal management on electric vehicle energy consumption and driving range. Electric vehicle thermal management is referring to systems that maintain the temperature of the cabin, battery, motor, and electronics in an EV. And these systems are the second largest contributor to the energy consumption of an EV. The goal of this work was to develop a modeling approach that can predict the impact of thermal management on energy consumption. And the approach we took is to couple a 0D open source EV energy consumption model with our commercial 3D heat transfer software, TAITherm. So I'll describe a high-level overview of the approach first, and then I'll go into more detail. The main input parameters are weather data, drive cycle, and EV parameters, and these are first fed into our 0D EV power consumption model, which is used to calculate the power consumed by the motor based on the drive cycle. Then that power consumption time series is used together with our 3D vehicle model and our battery thermal electrical model, along with Python code that models the control of the HVAC and thermal management systems for the motor and the battery. And from there, we calculate the power requirements needed for the HVAC and thermal management systems. Then we feed those power time series back into the 0D model and calculate the final power consumption results. So now I'll describe these parts in more detail, starting with the 0D energy consumption model. So those are these portions of the approach. For the 0D model, we adapted an open source Python package called the quantify, which calculates the energy needed to move a vehicle based on the drive cycle, and it tracks the energy consumption of all of the main components of an EV, like shown here. The inputs to this model are drive cycles, so speed versus time series. Two examples are here. Weather data and the EV parameters, which are shown in the table below. And we also modify the MAPA to take in the power consumption due to the thermal management systems that we calculate by our 3D model. As an output, the 0D model gives us the total power load time series and also the power loads and losses from the individual components of the EV. So here's some examples of the total power output. And we see here negative values correspond to the regenerative braking. And so we can see how the power varies during the drive. There are some limitations to MAPI, mainly around the cabin and HVAC modeling, because with the 0D model, it doesn't have a 3D cabin geometry with real material properties. It is not considering radiative heat transfer. It doesn't have a human model to calculate the sensible heat output contribution to cabin heating. The HVAC is controlled based on a target temperature instead of considering human comfort. And IMAPI doesn't consider latent heat, so doesn't consider condensation or evaporation that may be occurring on the human or in the cabin. So to address these limitations, we couple IMAPI with our commercial heat transfer software, TAITherm, and that's what I'll describe next. So in TAITherm, we create a 3D electric vehicle model. And so that is these portions of our approach. With our 3D model, TAITherm considers the impact of the environment on the vehicle temperatures. So that includes looking at the impact of the solar radiation and the ambient air temperature and the wind convection. Also considering the convection due to the vehicle's motion. So on the right are some animations from one of the simulations of a hot case. And we see once the car starts driving, due to the wind convection, the outside starts cooling, and due to the HVAC system, the inside of the car and the human temperatures reduce. And on the bottom right, we see the underside of the car showing the electric motor in the back and the full battery pack. And we see that with the thermal management systems, the battery pack temperatures are reduced down, so to the dark blue. And then they start increasing slightly a little bit later. So here's a zoom in of the battery pack with the liquid coolant loops. And on the bottom right, we see the green ribbons are the coolant loops, and then the blue cylinders are the individual cells of the battery pack. We modeled the battery state of charge and heat dissipation with a second order equivalent circuit model. And for the electric vehicle motor, we calculate the waste heat of the motor based on an efficiency versus torque lookup table. This can also be calculated by a more detailed empirical motor model. And then we take that waste heat and we impose it on the thermal model to calculate the motor temperatures. And we see an animation example here of motor heat up. So next, I'll describe the modeling of the EV HVAC load, which we do with our human thermal model. This is a model of a human composed of 20 body segments with layers representing tissues, and it predicts the tissue, blood, and core temperatures of the human, as well as thermal sensation and comfort. It's based on solving the bioheat transfer equation shown here, which is made up of the thermal diffusion term from standard thermal physics and 3 imposed heat terms on the right-hand side. These are a term to account for the metabolic heating of the human, a term to account for the heat exchange between the human and the environment, and a blood perfusion term accounting for the heat transfer due to blood flow in the body. And there are more details about this model in the paper referenced below. So we are accounting for all modes of heat transfer, radiation, convection is being considered by either a built-in empirical convection models, or also the model can be coupled with third-party CFD codes to determine heat transfer coefficients. And conduction is handled automatically across all physiological layers of the human and also clothing layers. We also automatically calculate latent heat transfer if evaporation or condensation is occurring, such as if the human is sweating. In this model, we can also account for differences in physiology, so male versus female, height, weight, and body fat percent, and population percentile. And we also can set an activity level describing what type of activity the human is doing and how much metabolic heat then they are producing. We have sweat distribution maps based on literature that describe how the sweat will appear on a human body. And we are able to track the sweat accumulation and report the amount of sweat that's accumulating as well. Also, we can consider the impact of clothing properties on human physiology by just setting the typical clothing parameters in the model setup. And so, as I mentioned, this model predicts the skin, tissue, blood, and core temperatures of the human. It also predicts the thermophysiology and thermoregulation aspects like sweat rates, shivering, and vasomotion. And finally, we also have sensation and comfort, which is very important for looking at how much HVAC power we need. So to model the HVAC, in this case, we are using a TAITherm fluid network, which is shown on the bottom right. So here we have 3 fluid nodes, 2 nodes representing the cabin air in the front and back, and 1 node representing the air inside of the HVAC system. And by imposing heat into or out of this HVAC fluid node, we can model heating or cooling. Then, based on CFD simulations, we defined flow speeds for the different parts of the body, and then we use our empirical convection models to model the convection heat transfer that the human experiences due to the HVAC system. We're using a PID controller and the human thermal model then to determine the amount of heating or cooling power that's needed to maintain a neutral thermal sensation during the drive cycle. So next I'll describe the modeling of the battery and motor thermal management systems. For that, we also use a fluid node network shown here. So we are using 4 fluid nodes. One represents the coolant at the coolant chiller or heater location. Another represents the coolant inside the battery. Another node represents the coolant inside the motor, and a 4th one represents the coolant inside the radiator. And then we implemented logic that will dynamically adjust the node connections and flow based on the scenario that we are in and the temperatures of the components of the EV. So for a heating scenario, we are heating the coolant at the coolant heater and then flowing that coolant past the battery and the motor and bypassing the radiator since we don't need a radiator for heating. The motor is being used, the waste heat of the motor is being used to help heat the coolant and the battery. For a coolant scenario, we have 2 possible scenarios. One is shown here, where the coolant is being cooled with a 2-phase cooling system, and then it is flowed past the battery and the motor and past the radiator. In the second coolant scenario, we have temperatures that are not as hot. So in this case, we can avoid using the energy of the 2-phase coolant system and just use the radiator to cool the coolant. And so we implemented thermal control logic to decide which operations to use and when, and that is shown here. And that's based on some chosen thresholds for the battery and the motor temperatures. So when the battery and motor temperatures are very hot, then we turn on the chiller to cool the coolant in most cases. And at moderate temperatures, we make decisions based on these criteria that are shown here. Next, I'll describe a bit about the model setup and automation. So we try to make this model easy to set up by creating this GUI to configure the EV. So here we can specify all of the vehicle parameters that are needed and the thermal management parameters. And we also have a small database of common EVs if you select from these drop-downs, then these vehicle parameters are already pre-filled based on data available online. Then the data that's entered into this GUI is saved into a configuration file, and then our code reads that data from the configuration file. We use our automation software TAITherm to automate the modeling workflow. So the coupling and running of the 0D model with TAITherm is done automatically with this simple TAITherm process. This run cabin model's blocks can be replaced inside with either a simple or a more complicated series of cabin models. So in a more simple case, you may have something like this, where we are just importing the boundary conditions like the clothing properties, the drive vehicle speed, power information, and information about the motor heating, and just running a single TAITherm simulation. Or it can be more complex, where we might be looking at a full day, for example. In this study, I was looking at starting the vehicle inside the garage to initialize the temperatures, and then having a morning commute, then having the car sit outside for 8 hours, and having an afternoon commute. So that also can be all automated with TAITherm. And this energy consumption process prototype will be available to try out soon. So now we'll describe a case study that we did. So we looked at an EV under 3 environmental conditions with the same city drive cycle. It was a 40-minute drive cycle. So the 3 conditions were a hot case where outside temperature was 38 Celsius, a warm case where it was 28 Celsius, and a cold case where the air was minus 10 Celsius. So looking at the hot case results, first looking at battery and motor thermal management. Here we are cooling the battery by the 2-phase cooling system. When it crosses the 35 Celsius thresholds, which happened at around the 3-minute mark. And then once it's cooled to below 35 Celsius, we stop using the 2-phase cooling system and are just running the coolant pump and radiator fan. So we see the animation of the battery and motor here. And then for the cabin thermal management, the thermal sensation starts off at hot, and as we run the AC here at maximum power, that sensation gets reduced down to near neutral by the end of the drive. And we see the temperature animation at the top here of the car being cooled, the outside being cooled because it is driving due to convection, and the inside being cooled by the HVAC system. Then looking at some more details about the coolant flow control. So at the battery, we have a situation here that sometimes the coolant temperature is actually hotter than the battery temperature. So in that case, we don't want to flow the coolant past the battery, since that would undesirably heat the battery. So that's why we have, sometimes you have to turn off the coolant flow, only flow it in certain parts. That is the downside of having this coolant in a single loop. For the motor, since the motor is the hottest component of our system, then the coolant always stays below the motor temperature, so we always flow the coolant past the motor. And then at the radiator, here the air temperature is also quite hot, so we have situations where the ambient air temperature is hotter than the coolant temperature, and in that case we turn off the coolant flow through the radiator, so we are not heating the coolant by the outside air. We also looked at the impact of flow rates on the hot case. So changing the coolant flow from 12 liters per minute to 6 milliliters per minute. We see the results here, where there was a slight increase in the battery and motor temperatures, and that caused us to need to turn on the chiller a second time towards the end of the run. Here it happened that our drive cycle ends very soon after we turned on the chiller, so this only caused a 0.7% higher energy consumption, but the impact would be greater if the drive was longer. We also looked at reducing the radiator airflow from 5 to 2.5 meters per second, so reducing the fan power. But we found that that had a minimum impact on the results and only reduced the power consumption by 0.3%. The radiator fan power is quite small and much smaller than the chiller power. So from this, the main focus for power optimization should be minimizing the time that the coolant needs to be cooled by the chiller. Looking at the cold case results, in this case, we are heating the battery with a 6 kilowatt resistive heater until it reaches 10 Celsius. And after that, we just use waste heat from the motor to continue helping to heat the battery. And we see the temperature animations at the bottom right. For the cabin thermal management, we are running the cabin heater at maximum power for most of the run. And once the thermal sensation gets to neutral, then we start ramping down the heater power. And we see the temperatures animations here, showing the cabin and the human temperatures increase. Then for the warm case, in this case, the battery doesn't need the two-phase cooling loop. And since the battery temperatures and motor temperatures are staying within the good operating ranges, the only power consumption is from running the coolant pump and radiator fans. AC here is used at a low to medium power, less than about 1 kilowatts, and it has no problem maintaining a near neutral thermal sensation. So here we see the power profiles for the three cases. In blue is the total power consumption for the EV, and we see that that closely follows the vehicle speed that's plotted in orange. And then the thermal management component of the power consumption is plotted with the dotted lines. So we see in the hot and cold cases a significant shift upwards in the power consumption due to the thermal management requirements. So comparing our scenarios, we found that for the hot case, the thermal management contributed 43% of the total energy consumption for the EV. It contributed 18% for the warm case and 50% for the cold case. So this is a table showing the total energy consumption in kilowatts and what that would correspond in terms of driving range for a Tesla-like car. And we see here that the cold condition in our simulations had double the consumption of the warm condition, and the hot condition consumption was 38% higher. We can see what components of the EV consume the energy, motor, HVAC, thermal management system, and then how much was regenerated from regenerative braking. In our simulation, the cold condition had higher consumption than the hot condition, partially because we assume that the cabin cooling system has a high coefficient of performance of 2, as is typical for AC systems. And then we assume here that cabin heating is done with resistive heat, which has a coefficient of performance of 1. So if the cabin heating was done with a heat pump, then we would see lower consumption on the cold scenarios. And here we also plotted the battery state of charge for the three scenarios, showing how it is depleted over the course of the drive. So to summarize this case study, we demonstrated combining a 3D heat transfer solver, human thermal comfort model, thermal electrical battery model, and 0D EV model for energy consumption analysis. And while this approach isn't a replacement for detailed EV component modeling, it can be useful for certain design studies, especially earlier in the design process. Through our example study, we demonstrated the significant impact of cabin and thermal management on EV energy consumption. So this motivates the importance of carefully considering thermal management when designing EVs. I want to end by mentioning some additional EV modeling options that we have beyond what I described today. We offer a comprehensive CIE toolbox with our flagship softwares being TAITherm and CoFirm, our automation software. And then we have a few extensions. The battery extension that I talked about, which models battery thermal electrical behavior. We have an exhaust extension that can be used to model internal combustion engines or hybrids, and the human comfort extension that I also discussed. And then CoFirm can also be used to couple with third-party tools like CFD or 1D system tools. So there are multiple EV cabin simulation methods available. Here are some that can be done standalone just with our software. So TAITherm can be run standalone with a fluid node network. And that is good for analysis of the cabin temperatures and comfort, but it doesn't tell you much about the energy consumption. So that's why in this study, we coupled it with a 0D energy consumption model with CoFirm. But also, if you want to focus more on the convection aspect of the modeling, you can use RapidFlow, which is our new fast 3D flow solver. So that might give a little bit more accuracy for the comfort predictions and energy consumptions. It's also possible to couple with a CFD tool using CoFirm, and additionally couple with 1D component models, such as a 1D HVAC model that may be more detailed than our 0D modeling approach. So that has the benefit of possibly additional accuracy for energy consumption and comfort prediction at the expense of additional runtime. So I'll describe this last one a little bit more. In this three-way coupling approach, we would have TAITherm modeling the cabin with the human model for the comfort predictions, and then we would be exchanging surface convection conditions from CFD into TAITherm, and TAITherm will be providing the thermal surface temperatures for the CFD. And then further, that can be coupled with a HVAC model that is very detailed, where you model the components of the HVAC in detail. For system modeling coupling, we have some new features that allow us to define coupling parameters of all of the portions of the model that you want to couple, and then the information can be exchanged with third-party system tools, and you can export co-simulation FMUs, a standard framework that is accepted by many third-party tools. So for more information, you can go to our website, or hear some references about EV modeling and human thermal model. Thank you for your attention, and I'm happy to take questions.
All right, thank you, Timothy. Let's go ahead and get to some questions here. Does the model also account for the impact of temperature on battery state of charge, and if so, how?
Yes, so we do account for impact of temperature on the battery electrical performance. When you set up a battery model, we define a configuration file for the equivalent circuit parameters of that model, and we define those parameters at a range of different temperatures, and then our model interpolates between those parameters based on the predicted temperatures. So that gives us the ability to model how the battery responds electrically to its temperature.
Okay, thank you. How long do these models take to run?
For this particular study that I showed with the case study, that model had about 350,000 elements, and running it on an 8-core processor took around 1 to 2 hours for the 40-minute drive cycle.
Okay, thank you. What is the reported human thermal sensation based on?
The thermal sensation that I showed for the case study here was using the Fiala dynamic thermal sensation model. That's a well-known model in the literature that bases sensation of the human on the core temperature, the mean skin temperature, and the rate of change of the mean skin temperatures. We also have a few other sensation and comfort metrics that TAITherm can output, such as the Berkeley sensation and comfort model. So there are different choices available.
Okay, well, looks like that'll do it for questions. So thank you, Timofey, and thank you all for attending. You will be receiving a follow-up email later today containing links to download the presentation slides and watch the recorded webinar session. Again, thank you all and have a nice day.